Chapter 51, Antimicrobial Effectiveness Testing of the United States Pharmacopoeia, has been in existence for quite some time. In fact, it was previously known as the Preservative Effectiveness Test. Along with considerable discussion pertaining to the USP test, we will also cover out-of-specification investigations when the AET test fails for our product under test, and we will briefly cover the use of the USP test for in-use studies. What is accomplished with this chapter is to examine antimicrobial effectiveness to ensure that the minimal required efficacy against microorganisms exists at levels of antimicrobial agents which are not in and of themselves toxic to humans. Because the chapter is written such that original unopened containers are required, it cannot be considered to be an in-use test directly. Some less than scrupulous manufacturers might be inclined to use an antimicrobial preservative to make up for inadequate microbial control. You cannot correct for faulty GMP by adding such agents to correct for sloppiness. A properly configured multi-use container should be designed to minimize the likelihood of microbial contamination. Most multi-use pharmaceutical products also require a preservative antimicrobial agent. What this means is how many USP monographs include a requirement for Chapter 51 testing. There used to be a number of USP monographs that included Chapter 51 as part of the testing requirements. These have been weeded out over time. Chapter 51, of course, has a number below 1,000, which means, according to the USP, that it is an enforceable chapter. Enforceable chapters are made so because they are referenced from within USP monographs. So, if there are no USP monograph references to this chapter, where else can I find in USP something that would make this chapter enforceable? Many USP scientific liaisons are introduced to general notices and requirements by their supervisors. It is almost considered to be a rite of passage, but it really does contain a lot of useful information. We will be covering these topics in order. There are many classes of preservatives, antimicrobial agents, available. Additional useful information can be found in USP Chapter 1072, Disinfectants and Antiseptics. Some ophthalmic products used to contain mercurials. These included a number of contact lens disinfectant products. To a large degree, these have been replaced with non-mercurial antimicrobial agents. Virtually every component of a microorganism can serve as a target for an antimicrobial agent. In Jurassic Park, there was a statement from the chaos expert along the lines of, "Life will find a way." Indeed, it will, and microorganisms have evolved and will continue to evolve strategies to deal with antimicrobial agents. Antimicrobial preservatives are substances that are added to non-sterile dosage forms in order to protect them from microbiological growth or to protect them from microorganisms that are introduced by accident during usage. Therefore, any non-sterile product might be suitable for including an antimicrobial agent. Also, sterile multi-use containers are generally required to have an antimicrobial agent. However, there have been some recent multi-use containers designed for sterile products. These are designed such that microbial contamination of the product within the container is prevented. Categories 1 and 2 have more stringent requirements than Categories 3 and 4. Categories 3 and 4 are for oral products and liquid antacids. Note that none of the categories are for non-aqueous products. A fair question is, why are the aqueous antacid products included in the product category with the least stringent requirements for passage, as you will see later? It turns out that such products tend to inactivate the antimicrobial agent over time, and given that a USP test is applicable throughout shelf life, many such products would fail the test. Antimicrobial agents wouldn't be very useful if they were not toxic to microorganisms. The risk, however, is that they might also have some toxicity to humans. Therefore, what is accomplished with this chapter is to examine antimicrobial effectiveness to ensure that the minimum required efficacy against microorganisms exists at levels of antimicrobial agents which are not, in and of themselves, toxic to humans. There is no way of knowing what sorts of microorganisms could pose a threat to a product over time and in the myriad of possible locations it could be used in. Therefore, a range of microorganisms is included spanning gram-positive and negatives along with 2 fungal species. This chart shows in highly simplified form the basics of performing the USP Antimicrobial Effectiveness Test. From time to time, people have considered adding all of the test species into the same container to be tested. This is not the proper approach because you then set up more of an experiment in microbial population interactions than a straightforward demonstration of antimicrobial efficacy. For products in categories 1 through 3, 10 to the 5th to 10 to the 6th CFU per mil are required. Category products require 10 to the 3 to 10 to the 4 CFU per mil. Here are the criteria that must be satisfied for each product category to pass the test. Note that the requirements are less stringent as you proceed from category 1 down to category 4. Also note that the requirements pertaining to fungi never exceed fungistasis. All of the product categories mention no increase from the initial calculated counts. The definition of no increase is not more than a half log unit higher than the previous value measured. Here above is an example of counts one might obtain as a portion of an antimicrobial effectiveness study. It turns out that you can have a measure of a 1500 CFU per mil compared to the previous value of 1000 CFU per mil, and that would indeed pass the test. Remember that an official test method in USP, be it in a general chapter or a monograph, is considered validated. However, it is often necessary to demonstrate that your particular product is suitable for use with the validated method. Given that USP microbiological testing is growth-based, it is necessary to demonstrate that test microorganisms can grow in the presence of your product following sufficient neutralization of the antimicrobial agent or agents. I know of a circumstance where a polymeric antimicrobial agent was used in an ophthalmic product. The analytical chemistry department developed a test for the agent that showed the concentration of the agent was almost absolutely constant over time. However, over that same period of time, the Chapter 51 test showed a steady decrease in efficacy. Which test was correct? Well, it turns out they were both correct. This polymeric agent agglomerates over time, creating what one could think of as being a molecular snowball. This meant that decreasing amounts of the agent were free to interact with the microorganisms. The analytical chemistry procedure first included a step that broke apart the snowballs. Because the polymeric molecules had not actually broken apart, they were indeed still all present, thus the steady concentrations chemically. The foregoing discussion about the polymeric antimicrobial agent describes what was found out during the investigation of the test failure using the polymeric antimicrobial agent in a product. What follows is a generic approach one could take following a test failure, an out-of-specification result. Remember that this validation is typically more along the lines of demonstrating method suitability. If you need to develop an addition to the method to bring about neutralization, that added portion may need to be validated as per Chapter 1227. The first bullet touches upon both method ruggedness and possible training issues. The second bullet touches upon proper GMP documentation practices. Remember that USP microbiological testing is growth-based. If the media cannot support growth, the test results are invalid. The first bullet pertains to the notion that genetic drift can occur, resulting in altered responsiveness to the antimicrobial agents. This notion has been the subject of some recent online debate. The general concern, again, pertains to the ability of the microorganisms to grow. Of particular interest in this list is the final bullet. Many people have asked about what constitutes the initial concentration, It is important to note that it is from the inoculum prior to addition to the product. Some have thought that it should come from a sample of product immediately after addition of the inoculum. This is ill-advised given the speed with which some antimicrobial agents can act. These bullets pertain in general to good GMP, and environmental monitoring is mentioned. Remember the previous discussion pertaining to the interplay of stability, analytical chemistry, and microbiology? Typically, one would expect the analytical chemistry and microbiology results to support each other, but surprises can be lurking. Clearly, Chapter 51 is a lab-based test, and products under test are not kept in the typical user's location. Can Chapter 51 testing be applicable to in-use testing? The chapter does provide for testing of products supplied in containers that are non-amenable to the test procedure. In such cases, 5 sterile capped bacteriological containers inert to the product may be used. This article directly addresses the possible use of a number of lab-based tests to evaluate in-use conditions. Unlike chapters 61, 62, 71, 85, and 1111, the Antimicrobial Effectiveness Test is not harmonized with the EP and JP. This stems from the fact that USP will not make a test official that will cause safely marketed products in the U.S. to become misbranded and adulterated due to failure to meet the test requirements. Back in the 1990s, a lot of work went into attempting to harmonize. The BP test passage requirements were more stringent pertaining to fungal species, and certain U.S. products could not meet the BP requirements. Thus, the test was never harmonized. There are, of course, many more types of antimicrobial agents to choose from. You would need to read the article for a discussion of what the in-use conditions tested were. The use of rapid microbiological methods has been the subject of considerable interest within industry and the compendia. Some of these methods are growth-based, others based upon biochemical capabilities, and still others based upon nucleic acid technologies.